Everybody, this will be a quick video on end behavior of power functions and polynomials. So really they're kind of like, that is the big crux of it, but we're going to talk about each of those three pieces. What is end behavior? What is a power function? What is a polynomial? How do they all kind of tie together? All right, so we'll start off with defining a power function. So a power function is any function of the form f of x equals kx to the p, where k and p are real numbers. So f of x equals kx to the p, so a couple of examples. That always makes things a little bit more easier to understand. 3x to the fifth. Yeah, that's a power function, kx to the p. What else do we have? 1/2 x to the ninth. Yep, 1/2 is a real number, 9 is a real number, kx to the p. Our old friend x squared. Yep. Let's see, what else do we have? Maybe some interesting ones. How about 4x to the negative 1/7? Yeah, 4 is a real number, negative 1/7 is a real number. Good to go. X to the negative 1? Yes, because, well, I guess this is the same as 1/x, but 1/x is equal to x to the negative 1, which is, yeah, good to go. 1 is a real number, negative 1 is a real number. Same with 1/x squared. This is the same as x to the negative 2. Also a real number. Okay, so there's power functions. How about end behavior? In particular, we'll look at end behavior of power functions, but end behavior just means it's basically like what's going on at the outer edges. What's going on as x goes to positive or negative infinity. That's all the end behavior means, the end points. Let x get really, really, really big in the positive direction. What happens to the function? Let x get really, really, really big in the negative direction. What happens to the function? That's all that end behavior is. So let's consider something like x squared. Well, so we want to think about what happens as x goes to infinity, what happens as x goes to negative infinity. So, and here's kind of how we write this, by the way. The notation is x arrow positive infinity. This says as x goes to infinity, we want to say what happens to f of x as x goes to infinity. And just think about it for half of a second. Think of some really large positive number, whatever number you like, probably something that you can still sort of like conceive of in your head. I might go for something like 10,000. When x is 10,000, f of x is 10,000 squared, which is very large. And that pattern is just going to continue. The larger that x gets, the even larger f of x ends up getting. So as x goes to infinity, as x gets huge, f of x, or x squared, also gets extremely huge. So as x goes to infinity, f of x also goes to infinity. And think about what the graph of x squared looks like. Like it just kind of trails off into the sunset. As x goes to infinity, that thing just like shoots off to the moon. So as x goes to infinity, f of x also goes to infinity. How about as x goes to negative infinity? What does f of x do? And again, think about it for a second. What is some somewhat large number in the negative direction? Maybe choose something like negative 10,000. What is negative 10,000 squared? It's really large, but is it really large and positive or really large and negative? It's really large and positive, because negative 10,000 squared is negative 10,000 times negative 10,000. A negative times a negative is positive. So negative 10,000 squared is actually the same as 10,000 squared. So as x goes to negative infinity, f of x also goes to positive infinity. This is the end behavior of x squared. is that as x goes to infinity, positive or negative infinity, f of x goes to positive infinity only. All right, well, what about x cubed? What happens with that? As x goes to infinity, well, again, think about it. If we plug in 10,000 into x cubed, 10,000 cubed is a really, really large number. So f of x, as x goes to infinity, as x gets huge, f of x gets really huge. F of x also goes to infinity. And take half a second before you just sort of answer this. What happens as x goes to negative infinity? What happens with x cubed as x goes to negative infinity? So again, think of a large number in the negative direction, like negative 10,000. Negative 10,000 cubed, and let me just kind of write this out. Negative 10,000 cubed is equal to negative 10,000 times negative 10,000 times negative 10,000. So these first two, negative 10,000 times negative 10,000, the product of that is some really large positive number. So now we have some really large positive number multiplied by negative 10,000. A positive times a negative is always a negative, which means that negative 10,000 cubed is a negative number, and it's a very large negative number. So as x goes to negative infinity, f of x goes to negative infinity. So the end behavior of x cubed is, as x goes to infinity, f of x goes to infinity. As x goes to negative infinity, f of x goes to negative infinity. Again, think about what the graph looks like. The graph of this thing, just as a reminder, looks something like this. Comes up right through the origin and then takes off. As x goes to infinity, f of x gets huge. As x goes to negative infinity, f of x gets huge in the negative direction. So that's the end behavior. And there is kind of like an easy way of thinking about this. I mean, if you have to, you can think about it exactly the way that I just explained it to you, which is, thinking about, well, what happens when we plug in a really large number into here? What is going to happen? But the other way is assuming that you're looking at a power function that has a positive degree. The degree means like what is the exponent. As long as those are positive, then you can kind of break it up. And I guess I should say there are like counterexamples. It's always kind of hard to say something universally in math because there are lots of little counterexamples. So I should say if it's a positive integer. Integer means a whole number. 1, 2, 3, 4, 5, 6, 7, 8. Those are the positive integers. As long as you're looking at the end behavior of a positive integer, it becomes very easy, the end behavior, because it mimics itself. In particular, if you have an even degree power function, then the endpoints are always going to point in the same direction. Just like what happens with x squared. The endpoints point in the same direction, whether that's positive infinity or negative infinity. Because what's the end behavior of negative x squared? Well, it's the same as the end behavior of x squared, but it gets flipped over the x-axis. So instead of going to positive infinity, now it's going to negative infinity. But in either case, the endpoints of an even function are pointing in the same direction. The endpoints of an odd function, though, where it has an odd degree, the endpoints point in different directions. One goes to positive infinity, one goes to negative infinity. Or if you think about negative x cubed, it just sort of flips this, so it would look like this, comes down like that. Then, still, it just flips. As x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to negative infinity. The endpoints point in different opposite directions. So if you're looking at a power function with some sort of positive integer power, you can just look at, is it even or is it odd? Is it, and then kind of think about, is there a negative in front of it? And then from there sort of deduce which direction the end behavior is going to point to. So that's kind of a nice quick way of determining the end behavior of a power function. Again, assuming that it has a positive integer degree. So if you're looking at some other ones that don't have positive integer degrees, like to the 1/7th power, you got to do a little bit extra thinking about what happens there. Or a negative power, you got to think about kind of what happens because it might be a little bit different. All right, next let's talk about polynomials. So let me give the definition of a polynomial. And the definition is a little bit cumbersome, but then when we look at some examples, it becomes really easy to understand. So a polynomial is any function of the form f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a sub 2 x squared plus a sub 1 x plus a naught, where n is a positive, I was going to say positive non-zero. I guess, yeah, positive integer. Maybe it would be better to say non-negative. That's what I should have said, not non-zero, non-negative. N is a positive integer, and each a sub I is a real number. So yeah, kind of a nasty definition. Some examples, though, make it look real easy. So something like f of x equals 2x squared plus 3x plus 1. That's it. Or how about something like x to the 8th minus 7x to the 4th? Yep, that's a polynomial. Our old friend x squared is a polynomial. Constant functions like f of x equals 2, those are also polynomials. So the big key about a polynomial is that the variables, any power on the variable is a non-negative integer. So they can't be negative up here, and they have to be whole numbers, 1, 2, 3, 4, 5, or 0. That's why something like f of x equals 2, the constant function, is a polynomial, because this is the same as 2 times x to the 0th power. Sometimes some textbooks will say, they'll tack on here, each a sub I is a real number, and a sub n is non-zero. And in that way they kind of try to exclude the 0 function from being a polynomial, but technically it is a polynomial. So what are some things, just for the contrast, that are not polynomials? Something like 1 over x to the negative 1, because that is negative. X to the 1/2, which is the same as the square root of x. Yeah, that's not a polynomial because this is not an integer. Any other good examples? Nah, that's about it. Well, I guess this one maybe. X to the 7th minus x to the negative 2nd. Again, because this is a negative power, it's not a polynomial, and this is the same as x to the 7th minus 1 over x squared. Yeah, not a polynomial. Okie dokie. Well, how about end behavior of polynomials? Can you take a guess? We can basically reduce a polynomial when it comes to end behavior. We can reduce it to a power function, and then from there we can talk about the end behavior. The reason is because the degree of a polynomial, the highest power, dominates it. So maybe I'll just write that as well as a definition. The degree of a polynomial, it's the highest power, and this is of a polynomial. The highest power of the polynomial. So with something like f of x equals x cubed plus 1, we say that's a degree 3 polynomial because the power is 3. f of x equals x to the 101 plus 45x to the 17th plus 9x plus 2. What's the degree of that? It's 101. Degree 101. It's the highest power. And the reason that the degree is important, in particular with end behavior, is because this degree, it completely dominates. Like as x gets really big in the positive direction or as x gets really big in the negative direction, the end behavior of this polynomial reduces to just the power function of whatever the degree is. So the end behavior of f of x equals x cubed plus 1 is the same as the end behavior of x cubed. The end behavior of this second function that I wrote is the exact same as the end behavior of x to the 101, 101st power. So, you know, like both of these, we can immediately say the endpoints are going to point in different directions. We just have to decide which direction does it go to positive infinity, which direction does it go to negative infinity. It would be the same thing too with, I guess, if I give an even function, an even polynomial or an even degree, 7x to the 6th plus 5x to the 5th minus 4x, whatever. This has an even degree, so both of the endpoints are going to point in the same direction. Either both of them go to positive infinity or both of them go to negative infinity, and that's kind of just your job, is to figure out where do they go. And again, it just kind of it all is going to reduce. If it's an odd power and it's positive, there's a positive coefficient, then as x goes to infinity, that function is going to go to positive infinity, and as x goes to negative infinity, that function goes to negative infinity. So with something like f of x equals 107x to the 91st plus, like, just whatever it is, just assume it's a polynomial in here, plus 3x minus 1, whatever it is, we can just think of this as 107x to the 91st power, which means that as x goes to positive infinity, f of x goes to positive infinity, and as x goes to negative infinity, f of x goes to negative infinity. It just reduces down like that. How about something like f of x equals, let's do some weird coefficients, pi x to the 44th power plus e x to the 41st power plus, what are some other weird numbers? Are there weird numbers? Why can I not think of any other strange numbers off the top of my head? I don't know. You can just come up with them. 1.73 x to the 8th. Something like that. Just whatever it is. You can just reduce this. What is it? Let's put a negative out front too, just to make it more interesting. Negative pi x to the 44th. How about that? What's the end behavior there? Well, it's even. So we know that both of the endpoints are going to go in the same direction. We just have to determine, do they go towards positive infinity or do they go towards negative infinity? Since there's this negative out front, they're both going to go towards negative infinity. So as x goes to plus or minus infinity, f of x is going to go to negative infinity. So, right, that's end behavior, that's power functions, that's polynomials. Let me know what questions you might have.